All right, welcome everyone to our final section 3.9 in-class video now. We are talking about antiderivatives. In our pre-class videos, we got all of our definitions of antiderivatives. We talked about initial value problems and what have you. And now we are going to expand on that and just see some more problems. But again, we have all of our definitions and theorems, so let's just see how we can apply these to more situations. Starting off with, we're finding the most general antiderivative for this function here. And the big thing that I want to go over again, and we saw this a little bit in the pre-class videos, is that rewriting when we have these radicals and what have you, right, into this form where we can actually use a power rule. So we need to remember, for instance, when we have the square root of x cubed, right? This is x cubed raised to the 1/2 power. And when you have powers raised to more powers, right, these things multiply. So this is really the same thing as x to the 3/2 power. So that's the 3 times the 1/2 there. Now that's just one part of this. We also have the cube root of x squared, right? So again, this really is x squared, and then we're raising that to the 1/3 power because, right, we're doing the cube root of that. Again, we have powers raised to more powers, and therefore they multiply, and this is going to be x to the 2/3. So this is a bit of algebra review before we even get to our calculus stuff. Right now, we're in a good position. We can find the most general antiderivative. I'm going to be doing this a little bit faster than I was doing it in the pre-class video, just because I do want to push you guys to kind of get faster at doing your antiderivatives. But if at any point, right, you're getting a little bit lost or confused or what have you, right, please do go back to the pre-class videos and just rewatch these because I do it a lot slower there. So, okay, most general antiderivative, quite often I'm writing this as a capital F for an antiderivative. I'm going to raise my power by 1 because let's see, right, I have 3/2. This should go to 5/2 because when I take the derivative of it using the power rule, I need to go back down by 1 to 3/2. And then I multiply by the reciprocal here. So instead of 5/2, I'm going to have 2/5. And of course, we can double check pretty fast here. If I take the derivative of this, I should get back to where we started. I'd have 2/5 times 5/2, and I reduce my power by 1. So instead of 5/2, I'm going to have 3/2. Notice that the reciprocal means that these will perfectly cancel out, and I'll be left with what I started with, x to the 3/2. So that seems to have worked out quite well. Let's do this one more time. We're going to raise our power by 1. So instead of 2/3 here, I'm going to write 5/3, and then I'm going to multiply by the reciprocal. That's going to be 3/5. So we can double check just to be a little bit paranoid, a little bit concerned, right? Maybe we've made a small mistake. But when I take the derivative of this, we're going to have this 3/5 along for the ride. X to the 5/3, this 5/3 will come down, and then we need to reduce our power by 1. So instead of 5/3, right, this is going to be 2/3. Again, because we have this reciprocal, these are going to nicely cancel out, and we're going to be left with exactly what we started with. Now, this is an antiderivative, but if we wanted the most general antiderivative, we're going to include in a plus c, meaning that really you can have any old constant. This could be +5, +7, plus pi, minus 100, whatever you want, right? Because when you take the derivative of the constant, you get back to 0. And so any of these would be perfectly fine antiderivatives. So this right here is the most general antiderivative, is when you include that plus c. All right, let's do it again. Find the most general antiderivative for this function. This one, I would invite you to pause the video, try this one out on your own, see how far you can get. And then once you're happy, come back and hear the answer. All right, let's get to it. So we're going to go ahead. I'm going to use capital G here, I suppose, for an antiderivative. I'm going to, again, start off with maybe 4x squared, because double check, if I take the derivative of this, I do get down to 8x. Again, I'm doing a couple of steps kind of in my head now that, again, in the pre-class video, we took this a bit slower, but we need something that when I take the derivative of that, I get 8x. So I'm going to need to have like an x squared. But if I take the derivative of an x squared, right, a 2 comes down. So notice I had to adjust from an 8 to a 4 here, basically dividing by 2. So that way, when I take the derivative, I do get back to where I started. Now, this -3 is along for the ride, and I need something that when I take the derivative of it, I get secant squared. So again, I need to think back to my chapter 2 days and taking derivatives of trig functions, and you probably will recall, right, that if you take the derivative of tangent, you get secant squared. So this will work out perfectly well. So -3 and secant squared. Excellent. And then if I want the most general antiderivative function, I'm going to include in this plus c just to just stand for, right, that I could have plus any old constant here. It could be a +5 or it could be a -13 or whatever, right? Any old constant would also make an antiderivative. So this is the set of really what all the antiderivatives look like for this particular function. All right, kicking it up a notch in our difficulty level here. Now we have something where there's a bit of division, and we saw one in our pre-class video where we had multiplication. It's going to be a similar sort of storyline here, is that we don't have a product rule, or likewise here a quotient rule, when it comes to antiderivatives, right? And so we need to figure out a way to simplify this first before we start taking the antiderivative, because again, we don't have a product rule or a quotient rule for antiderivatives. We also are looking for not just the most general antiderivative in this problem, but we're looking for an antiderivative that also satisfies some initial conditions. So these were called initial value problems, and we talked about these really in our second pre-class video. So again, if you need a review, feel free to go back to that, but we're going to basically be solving for that C, the right C that solves, right, when we plug in 1, we should get out 6. So before I even start taking the antiderivative, I need to deal with the fact that I have a quotient here, and I'm going to distribute this division by root t. So I'm going to have 3 divided by root t minus t divided by root t, and then I have plus t squared divided by root t. So each one of these things needs divided by root t. Now remember, this is really, this square root of t is t to the 1/2 power. And so we could take one more line here. And then we need to get into some quotient rules, right, when we're taking and simplifying this. But let's go ahead and first just do a little bit of a rewrite. And now we need to know how these things cancel out, right? Because technically, for instance, we have a t to the first here. And so we have some cancellation that's going to happen because we have like bases. And just like when we're multiplying like bases, you would add exponents. Here, when we're dividing like bases, you subtract exponents, right? So for instance, we're going to have t to the 1 minus 1/2 there. And likewise here, we're going to have t to the 2 minus 1/2. So because we're dividing, we subtract our exponents. We can write this first one as 3t to the negative 1/2. For instance, it's like t to the 0 minus 1/2. Or right, there's a different rule for exponents that just tells you this very quickly. So any of these are perfectly good. Let's go ahead and also simplify in this line. So 1 minus 1/2 is going to be 1/2, and 2 minus 1/2 is going to be 1.5, aka in the fraction form, 3/2. So now I've got this all set up using, really well set up to use our power rule on in order to find an antiderivative. So far I haven't done any antiderivative. I've just been rewriting my little h. So now let's go ahead and find an antiderivative. And so let's see, the 3 is going to be along for the ride. I'm going to increase my power by 1, thinking about something that when I take the derivative of it, I need to get back to where I started. And then I need to multiply by a reciprocal, right? So something like the reciprocal of 1/2 is going to be 2. So I'll go ahead and try that out. Let's do another one here. I'm going to have t raised to the 3/2, right? That's after I increase my power by 1. And I'll include the reciprocal of my new power there. That's going to be 2/3. And one more time, I'm going to increase my power by 1. So instead of 3/2, I'm going to have 5/2. It's a little bit of typo. And then I'm going to multiply by my reciprocal. So in this case, 2/5. So this is what I think is a pretty good antiderivative. I include in my plus C for the most general antiderivative, but let's be a little bit concerned and paranoid and worried about if we made a mistake. So I'm going to go ahead and just check really quick and make sure that if I take the derivative, I get back to where I started. So if I take the derivative of this, let's see, we have 3 times 2 times, when I take the derivative of this, the 1/2 power would need to come down, and then I'd have t to the negative 1/2. So this is nice. The 2 and the 1/2 do perfectly cancel out. Here I have negative 2/3. That's a constant along for the ride. When I take the derivative, we have the 3/2 comes down, and I reduce my power by 1. So instead of 1.5, I just have a half. And again, we have some cancellation. That's nice. And then finally, we have this 2/5. That's a constant along for the ride. When I take the derivative, the 5/2 comes down, and then I reduce my power by 1. So instead of 2.5, we have 1.5, aka 3/2. And when I take the derivative of any constant, we just get 0. So again, there's a bit of cancellation. And we can see that this 3t to the negative 1/2. I wanted that. I wanted negative t to the 1/2. I got that. And I want plus t to the 3/2. I have that. So this is exactly what I started with. So therefore, I have a good antiderivative, something that when I take the derivative of it, I get back to this function that I'm interested in. So this is my antiderivative, but notice that I don't want just the most general antiderivative. I do want a antiderivative that when I plug in 1 into it, I get out 6. So I need to solve for that c value that makes this true. So I'm going to go ahead and look at my antiderivative here. I'm going to plug in 1 into this. I suppose I'll go ahead and simplify. 3 times 2 is going to be 6. And then I'm going to have 1 raised to the 1/2 minus 2/3, 1 raised to the 3/2, and then plus 2/5 and 1 raised to the 5/2. And when I do that, when I plug in 1, I ought to get out 6. And I have this plus c that I forgot to write down. All right, so this is my setup, and with this, I should be able to solve it. My only unknown there is c. And so let's see. The nice thing about when you take 1 and you raise it to powers, right, it just stays 1. So whether you're taking the square root, aka the 1/2 power, right, it stays 1. Or if you're doing other powers, right? So this is just going to be 1 here, 1 raised to the 3/2. Your calculator will verify that's 1. 1 raised to the 5/2, right? When you take 1 and you raise it to various powers, it stays 1. So that's nice. And so we're going to get that my equation becomes 6 minus 2/3 plus 2/5 plus c is again supposed to be equal to 6. I can go ahead and subtract 6 on both sides, so I get something like that. And then finally, let's go ahead and rearrange this, and I'm going to have 2/3 minus 2/5 should be equal to my c. And if I was doing like a web work problem or something like this, I would just leave it just like this. I understand that you can get a common denominator and simplify maybe a little bit farther. But again, we're in a calculus class. We're not in an arithmetic or an algebra class. And so this is perfectly fine to leave it in this form. So 2/3 minus 2/5 is my c. So now all I need to do is plug that back in up to where I have my c here. So let's see, I'm going to have h of t is equal to 6t to the 1/2 minus 2/3 t to the 3/2 plus 2/5 t to the 5/2, and then plus my c, which again was 2/3 minus 2/5. So a little bit scrunched down in here. Apologize for that, but that right there is my final answer. This is my function that when I would take the derivative of it, I get where we started. And if I plug in 1 into this, we get out 6. So it satisfies both of these things, and therefore I have it's completely solved our initial condition or our initial value problem. All right, so pause here just to let everyone catch up. But we're going to have another one. This one just says outright that it's an initial value problem. And we just need to remember that when it says something like this, right, we're looking for this function. And that's how we're going to solve this, is finding this function that satisfies both of these conditions. So we want it to, if we take the derivative of it, we get this. And if we plug in 4, we should get out the answer of 20. So again, I'd like you to try this one on your own. Try to find a function that satisfies both of these things, aka solve this initial value problem. Get as far as you can, and then when you're ready to see the solutions, come on back. All right. Well, you can see that I went ahead and hopefully while you pause the video, wrote out my answer for this problem. But let's go ahead and talk through this. But if you got the answer of 4x to the 1/2 plus 12, then I think you're on the right track. So again, the first thing I did was a bit of a rewrite here. I decided to rewrite this division by the square root of x as x to the negative 1/2 power. So right, you need to remember your rules for exponents. This 1/2 power is the same thing as the square root, and the fact that it's division or in the denominator, right, that means you're going to have a negative sign. And so that is what our function looks like, kind of in its exponent form. Now we need to find the antiderivative using the power rule. So I'm going to raise my power by 1. So instead of negative 1/2, it's going to go to positive 1/2. And then I need to multiply by the reciprocal. So instead of 1/2, right, I'm multiplying by 2. So that's where this 2 comes from here. And the most general antiderivative is going to include in a plus c. Of course, I want to find a very specific c, so that way if I plug in 4 into my function, I should get out 20. So if I plug in 4 for x, my output in that case should be 20. Notice I did do a little bit of simplification. 2 times 2 is of course 4. And then I plugged in 4 and got out 20. So in order to make that a true statement, right, I needed my c to be equal to 12. So of course the 4 to the 1/2 power, that's the same thing as the square root of 4, that's 2. 4 times 2 is 8. Subtract that off of 20, that gives me the 12. So after all that, right, plugging that back in for my final answer, that's how I got this f of x. So this is this unknown function that satisfies both conditions, right? When you plug in 4, you get out 20. And also if you take the derivative of it, you get 2 over root x. And of course we can check both of those things. All right, so that is solving the initial value problem. And again, you just need to kind of remember that phrasing, right? What it means, solve an initial value problem, it means go out and find this mysterious function that satisfies these conditions. All right, now more from the kind of an application-y standpoint, right? We can also be given things that we know are derivatives. For instance, here is an acceleration function, and we are given some conditions, right? If I plug in 1 into position, I get out 20. And if I plug in 0 into our position function, we get out 0. So the big thing is that you need to remember that acceleration, this is the same thing as the second derivative of position, right? Normally, if you take the derivative of position, you get velocity. And if you take the derivative yet again, now of velocity, you get to acceleration. So this is actually a second derivative. And we are interested in position, right? We have information about positions here, and the problem says, right, find the position of the particle given this data. So I'm actually going to want to take 2 antiderivatives, right? Each one will cancel out one of my derivatives, and that will give me back to position. So let's go ahead and do this one together. Maybe first off, if I take one antiderivative, let's see, I'm going to need to raise my power by 1. So t cubed, and then multiply by my reciprocal. Let's go ahead and raise my power by 1 here. So instead of t to the first power, I have t squared, multiply by my reciprocal. And we'll go ahead and simplify down here in one line. So 4 times 1/2 is going to be 2. And then plus 6t. So that's the antiderivative of 6. And again, technically there's plus a constant, and we'll need to solve for that a little bit later, but I don't have any information to plug in right now about what happens for s prime of t, or aka velocity, right? I have 2 pieces of information that are both related to position, right? When I plug in 1, I get out 20, and when I plug in 0, I get out 0. So that being said, I'm going to need to do one more antiderivative to get something about position. So let's do this one more time. We have this 1/3 that's along for the ride. When I take an antiderivative of t cubed, I'm going to need to raise my power by 1 and then multiply by the reciprocal. When I take the antiderivative of t squared, I'm going to have t cubed and then multiply by the reciprocal, 1/3. We're going to have 6, and instead of t to the first power, this is going to become t squared, right? Raising my power by 1 and then multiplying by the reciprocal. And this is where it gets a little bit complicated, right? Now we have this constant c. And you can imagine it, you know, as like a 5 or a 13 or what have you. But when you take the antiderivative of a constant, right, you're going to get that constant times t. So just like back here, when we took the antiderivative of 6, right, we got 6t, right? The 6 was a constant, and when we took the antiderivative, we got 6t, right? And of course, we can check, right? When we take the derivative of 6t, we get back to where we started. So if we want to have this constant c, this needs to be ct. And then when we do an antiderivative, the most general form is going to be plus a constant. And now you have to be a little bit careful about this, because if we just use the same notation, if we just use a c here, this kind of implies that they're the same constant, but there's no reason that these 2 c's would have to be the same. And so we need to kind of denote that they could be different than one another. So you can use, I prefer typically to use c and d. You could also use subscripts. if you're big into physics and whatnot, I know that, C sub 1, C sub 2, all that sort of stuff are perfectly fine. But I'm just going to use a different constant, in this case, capital D, to denote that it's still constant, but it could be different than the one that I started with. There's no reason that they both have to be 3 or they both have to be 5 or anything like this. So it's important that you label these differently. All right, so now I have all of my antiderivative work. I could clean this up with a line, but I'll have opportunities doing that moving forward. I want to figure out what these unknown constants are, and I have two pieces of information. One is if I plug in 0, I get out 0, and the other is if I plug in 1, I get out 20. So let's go ahead. I like zeros personally, so I'm going to go ahead and start plugging in zeros. So if I plug in 0 here, let's see, this is going to be 1/12, 0 to the 4th, minus 2/3, 0 cubed, plus 3, 0 squared, plus c times 0 plus d. And when I plug in 0, I'm supposed to get out 0. So in this case, I mean, anything times 0 is just 0. So I mean, this is going to be going away. This is 0. This is 0. This is 0. Even c times 0, I don't know what c is, but when I multiply by 0, it's going to be 0. So all of this stuff is going away. And what I'm going to be left with is a statement that says that d is equal to 0. All right. Well, so that means as of right now, I know that I have my position being 1/12 t to the 4th minus 2/3 t cubed plus 3t squared plus ct, and d was equal to 0. So this is going to be plus 0. So this is as much information as I have right now, but I also have one other piece of information that is when I plug in 1, I ought to get out 20. And so let's go ahead and use that to hopefully solve for this unknown c. So if I plug in 1, so 1 to the 4th is just going to be 1. 1 cubed is just going to be 1. 1 squared is just going to be 1. And this is going to be c times 1. So that's me plugging in 1 everywhere I see a t. I'm supposed to get out 20. And so let's see. The only one that's not a fraction here is this 3, I suppose. So I'm going to have, what, 17 plus 2/3 minus 1/12. That's what my c is. And so, well, it's not very beautiful. And again, you could spend some time simplifying this down, but I'm going to resist that urge. And I'm just going to go ahead and plug this in to my final answer. So again, everywhere that I have a c, I'm going to go ahead and plug in this constant here, and that'll be my final result. So let's go ahead and do that. So my position function is going to be 1/12 t to the 4th minus 2/3 t cubed plus 3t squared. And then my constant here, which is 17 plus 2/3 minus 1/12. And this constant needs to be next to the t. That's the one that we've integrated next to. Sorry, taking the antiderivative. Spoilers. All right, there is my final answer for solving a position, which again, really is an antiderivative. So we have solved some initial value problem in this case. All right, I wanted to do one more of this same sort of flavor, but the wording is different. And I remember we have a problem in our homework, web work, that has similar wording to this. And so I just wanted to kind of illustrate that this is more of from a graphical standpoint, right? We've kind of done the pure algebraic stuff or pure formulaic where we have just a formula is given and we're saying, hey, solve this initial value problem. This feels like a very pure math question. We have kind of more of the application-y stuff, right? That, hey, this can be used to find position if you're given acceleration, right? So this is kind of the more application stuff. And this is the more graphical. Even though you don't see a graph, right? The words here are all kind of talking about points on curves and graphs and whatnot. So let's read through this one. We have a curve y equals f of x goes through a specific point. The slope of its tangent line, given at any point, is given by this equation. Now remember, slope of a tangent line, right? This is supposed to be the derivative. So this is just a fancy word to say, hey, this right here is my derivative function. And I would like to find f of x. So we are given a derivative function and we're given a point that is supposed to be on this curve. Another way to write this is that when you plug in 1, you should get out 0, right? So really, this is just an initial value problem, but the setup, the wording's a little bit different. So it takes a second to kind of interpret this. Again, this is kind of given as far as graphs are concerned. We're talking about slopes on a graph, and we're talking about points that it goes through. But these can be converted into kind of algebraic statements or statements with functions and equations and what have you. So okay, we have a derivative function, and we have a point that it goes through. This is really some initial condition, or an initial value problem. So again, we want to find f of x. So now that we have it set up like this, it becomes a lot more standard. So let's do this one together. First thing I'm going to go ahead and do is a quick rewrite. Just instead of the square root, I'm going to write x to the 1/2. That way I'm well set up to use the power rule. Think about the power rule. I'm going to do an antiderivative now. Raising this. Instead of 1/2, we have 3/2. So when we raise it by 1, and then we're going to multiply by the reciprocal, 2/3 minus x plus some c for the most general antiderivative. And then we're going to solve for that, because when we plug in 1, we need to get out 0. So if I plug in 1, let's see, going to be a little bit of cancellation here. 2 times 2 is going to be 4. 1 raised to any power is going to be 1. And when I plug in 1, I should get out 0 here. So this is going to be 1/3 plus 4 minus 1. I guess I can simplify that down to just 3. Plus c should be equal to 0. So if I go ahead and rearrange, I'm going to have c is equal to -3 minus 1/3. And again, if you'd like to, you can spend some time simplifying this, right? What -3 would be the same thing as 9/3. If we subtract away 1 more, this is going to be -10/3. But you can also leave it and plug it into our homework system and all that sort of stuff, just as -3 minus 1/3. So that's also perfectly fine. But I'm going to go ahead and plug this in up here and write down my final answer. So f of x is equal to 1/3 x cubed plus 4x to the 3/2 minus 10/3. And this is a function that you can verify when you plug in 1 into it. It goes to the point 1, 0. It'll output 0 for you. And if you take the derivative of it, aka find the slope of the tangent line, the slope of the tangent line gives you exactly this function here. So this satisfies both the conditions that we were given. All right, we have one more page to go. These ones are slightly different problems than maybe we've seen before. Again, kind of thinking and inching towards the graphical standpoint. We can also talk about, and we've done in chapter 3, right, graphing derivative functions if we have the original function. And we can also go backwards on this, right? So I'd like to sketch an antiderivative given this function here. So I have a function, a little bit discontinuous and what have you, and I'd like to sketch an antiderivative of this function here. And so we need to remember and basically be thinking about that this is giving us derivative information. Again, we need to sketch some capital F here, and its derivative is little f. So when I'm looking at this, really I'm thinking about, I'm given a derivative and I want to know what kind of function, what does it look like that gave me something like this? Okay, so I don't know where I start, because again, for an antiderivative, you can have any old plus c. So I'm going to go ahead and say we're going to start at the origin. We're going to start at 0, 0. That seems to be kind of the nicest version quite often, and go from there. So the first thing that I need to see is that my slope is positive. I don't know exactly how high this is, but at 0, my slope is positive. So I could just do a little line here, for instance, to denote that I'm going to be going up. My slope is positive, but my slope seems to be kind of teetering out, right? As I continue and I head towards 1, it ends up flattening out. My slope goes down and ends up being 0. So a little bit later here, my slope's going to be, a little bit flatter. And then at 0, my slope's going to be, at 1, my slope's going to be completely flat. It's going to be a slope of 0. So I could do a function sort of like this. And I guess I really shouldn't go beyond 1 quite yet, but something like this where, again, it starts off positive. I know that. It gets a little bit, more shallow. It doesn't increase as fast, and then it flattens out around 1. Now, after that, seems like we make a bit of a jump and our slope ends up being negative, and it looks like it's constantly that whatever it is there, maybe this is like a slope of -1, right? It's nice and constant for a little while up until we hit 2. So, okay, my slope's going to be negative. So maybe something like this, and it's going to keep on being negative up until I hit 2. So, and again, it's constant slope, which means we're going to have a straight line here. So something like that. Now, again, yours may look a little bit different, and right, I chose this negative slope here, but I mean, you could have said, well, I know it's constant, I know it's negative, and go even farther down, or you may say, well, maybe it doesn't go that far down, maybe it goes something like this. But the big thing here is that it's a negative slope and it's constant, so it's made a straight line. So there's some things that we can't get perfect with this because, again, we're just doing a sketch, so it's not going to be a perfect representation, but really we're looking more at the qualities or the characteristics of our graph here. So it should be going down and it should be at a constant slope. So something like this. All right. Then what happens? Well, at between 2 and 3, we start to have our slope go a little bit more towards 0, right? It's still negative. We still have a negative slope, but it's kind of flattening out a little bit. It's kind of going towards 0. So here I would still have a negative slope, but maybe it's kind of, again, not as steep. And then at 3, it's going to be 0. So it's going to be a nice horizontal tangent line. So something like this, where, again, kind of flattening out. We still have a negative slope. However, we're flattening out, and eventually we're going to have a slope of 0. So it's going to be nice and flat here. So again, this is a graph of the derivative. We have a negative slope, and you can assign numbers to this, even though, I mean, there's not really numbers here, but I mean, you could say that this is a slope of -1. So this could be a slope of -0.7. This could be -0.5. But again, the slope's negative for all of these things. And so we should still be going down when it comes to our actual function. And this is sometimes where it takes a little bit to kind of wrap our heads around it. I mean, similar to when we were doing this earlier in chapter 3, when we had a function and we were graphing its derivative, right? This took a little bit of time to kind of really understand. But here we have a picture of what the slope is supposed to be doing on our function capital F. Now, after 3, it looks like our slope continues to rise, and now it's positive all the way up to 4. And then we need to kind of stop and reconsider. But okay, so we're going to have a positive slope from 3 to 4, and it seems to be getting more and more positive, right? So this continues to go up. So we're going to have a positive slope from 3 to 4, and it seems to be getting more and more positive. So maybe something like this. And again, if we were to kind of graph little tangent lines, starts off, our tangent line is horizontal, it has a slope of 0. Then it starts to increase a little bit more, then it starts to increase a little bit more, right? Our slope's increasing all the way until we hit 4. So again, on here, we have a slope, it's increasing, it gets getting bigger and bigger, and then at 4 kind of it stops and we need to reconsider. All right. And lastly, from 4 to 5, we have a little bit of a picture. The slope, it looks like it's positive, right? Because again, this is a graph of our derivative function. So again, from 4 to 5, our slope is positive, but it seems to be getting less and less positive, right? And at 5, it flattens out, and we'll have a slope of 0. So, okay, I think it's going to look something like this, I would suspect. So we still have pretty positive slope, less positive, less positive, less positive, and then at 5, it's going to be nice and flat. So again, the big thing here is when we have a function and we're trying to graph its antiderivative, we really consider that to be a derivative, right, of our antiderivative. And so we need to kind of think of this as slope. And when we think about it as slope and try to graph these slopes, right, we get a function that looks like this. So let me go ahead and erase these little green tangent lines, but this is how I would graph a function like this. And you can also notice, for instance, on our function here, right, we have a local minimum. And we could talk about why 1 is a maximum over there. But let's just look at this local minimum. Notice that our slope was going down. It was negative, right? We had negative slope. And then we have positive slope up here. On our derivative picture, right, this is supposed to be a picture of slope. We have negative slope. It's below our x-axis, right? So maybe this is -1 and this is -0.5 and all that sort of stuff. And then our slope becomes positive, right? And so, yes, there should be a minimum there. And so there's certain characteristics, even though, again, this is an antiderivative. It's not like we can graph the only correct answer, but this is a good sketch for an antiderivative. But all of them should have minimums, for instance. So that's kind of nifty. All right. Well, so there is a different type of problem, again, really from a graphical standpoint, saying that, just like we did the graphs in the one direction, earlier in chapter 3, you can do them now with antiderivatives as well. If you wanted to, you could also pose this in terms of velocities and positions and all that sort of stuff, right? Rather than just saying, here is a derivative, find an antiderivative, right? We could say, for instance, that our little f is velocity. And we could say graph a position function. And then you probably wouldn't even use little f, right? You would probably, instead of doing this, you'd say this is maybe v of t. So this is our velocity here, and find position or sketch a position function. Or likewise, you could do maybe f is acceleration. Graph a velocity. So here's an alternate option, right? So again, you just need to remember that acceleration is the derivative of velocity. So you're given a derivative function and you want to find kind of where did you start, aka an antiderivative. All right, the last thing that I wanted to do in our class time here is to do a couple of true falses, just because I know that these can be a little bit tricky sometimes. And so here are 3 true falses. We'll also justify our answers. I'll probably just do it with my words, but give you an idea of what you could write down. If you were come across something like this on a quiz or an exam or anything. So identify which statements are true and false, justify our reason. So, okay, we're going to start off one by one. Statement A, if f of x is an antiderivative of some little f, then capital F of x plus 3 is also an antiderivative. So yeah, that's going to be true because, right, if you take the derivative of f of x plus 3, so plus 3, well, you're going to have f prime of x plus the derivative of 3 is just 0. And because right, we know that capital F is an antiderivative of little f, therefore we're going to have little f here, right? This f prime, something that when you take the derivative of it, you get back to where you started. You get this little f. And so, yes, we have this other one, when we include this plus 3, also when you take the derivative of that, you get back to where you started with. You get this f of x. Another way to say this is that, this is just some plus c, right? So we have plus 3 here, but it could have been a plus 5 or a plus 9 or -7, whatever, right? But this is just some plus c. This is just kind of one of the antiderivatives. Because the most general one includes any constant, right? So all of these, that when you take the derivative of them, you get back to your original function, little f. So yep, this one is going to be true. Next up, statement B. The antiderivative of a non-zero constant function is itself a constant function. All right, so a little bit to unpack here. A non-zero constant function. So, and we have something that we need to take the antiderivative. So I'm going to go ahead and just try to do an example here. So a non-zero constant function, I'm going to use 5, right? And I need to find the antiderivative And my claim is this also constant, right? Is itself a constant function? Well, if I find the antiderivative of this is going to be like 5x plus some constant, right? So if I do the most general one, but that's not constant, right? So while my while my original function may be constant, my antiderivative, right, it has to include that x. And so this is going to be false. So a counter example is going to be little f is 5, then capital F is 5x. This will just be an antiderivative, we'll say, and this is not constant. Certainly has constants in it, but it itself is not constant. It's a linear function, right? If we were to sketch a constant function, it would be just a nice flat line, but a linear function, right? This is going to have a positive slope. And so, nope, this one is not a constant function. It's changing with time. So second one here is false. And then a third final example, we have little f is continuous, then every antiderivative of little f must be increasing. So it's continuous, but also it's positive. I guess that's an important point here. And so if we have an antiderivative, right, we're talking about and are interested in a capital F. And remember, capital F is something that when you take the derivative of it, you get back to where you started. So this thing we know is supposed to be positive. So therefore, right, the derivative of capital F is supposed to be positive. So if our derivative is positive, well, again, the question is something about, is this increasing or not? Well, that's exactly true, right? Back from earlier in chapter 3, right? When we have a positive slope or a positive derivative, that means that our original function was increasing. So this is going to be a true statement. So slope is positive. Therefore, function is increasing, right? If it has a positive slope, it needs to be going up. So it's an increasing function. So there we are. There's a few true false questions that again are a little bit more conceptual. But again, we just need to kind of take our time with these, think about our definitions and apply what we know. All right. I hope you found this useful and good luck, and I'll see you in chapter 4.